All right, in this video, we're going to talk about the properties of logs. You can actually find this exact picture in your textbook at the beginning of the section 3.3. All right, so there's two types of properties, or two types of logs that we deal with, these three properties. Logs are with any base, right? So base of A, and that A is a positive number, so it's basically any number larger than 0, and it can't be equal to 1. Or we have natural logs. So remember, all of the natural logs already have a base of E. Okay, so our three properties are known as the product property, the quotient property, and the power property. Notice that for all three of these properties, we're dealing with monomials. So UV is a monomial. U over V, again, monomial. U to the power of N, monomial. This one, it's the first two that we want to make sure that we focus on, that they're monomials. So anytime we see things being multiplied together, we can separate them using an addition sign. Anytime we see things being divided by one another, we can see that we are separating them through a subtraction sign. And in the power property, we can bring what's ever in the exponent down in front of our logs. Now, where we're talking about this, I want to make it quite clear about the quotient property, because that's the one people tend to forget about or make mistakes on. If you have the log of U over V, notice that it is a fraction next to the log. This is not the same as log of U divided by log of V. These mean two very different things. These are two logs, while this is a single log. Also, this is not equal to log of U just divided by V. So we want to make sure that we're very careful and clear about this information. Okay, so I want to show you via the calculator that this is actually true. So I'm just, for calculator's sake, I'm going to let U equal 2, and I'm going to say V is equal to 3. So if I do this, I'm going to say log, and I'm immediately just going to say 2 divided by 3. Close my parentheses, and notice I get a lovely decimal that's negative. So what happens if I write it as log of 2 divided by log of 3? Notice that we're going to get a very different answer, still a decimal, 0.63. So notice they're not equal to each other. And then if we try the last one, log of 2, but I close my parentheses and I just divided it by 3. Again, notice that we get a completely different answer. Okay, so it really pays to pay attention to how we are writing out our answer, because these are three different ways to write out three different answers. Okay, now if I actually use our quotient property and I actually try doing log of 2 minus log of 3, we should get, if I press enter, we should get that same answer of 0.176 negative. So let's see what happens. And again, notice that it's negative 0.176. So it gives us the same answer. Okay. Now, something to also keep in mind, all of these properties actually came from knowing your exponent rules. So what I want to do is I want to just do a quick little proof of the first property. So proof of the product property. Now, this is not something that I'm going to test you on or have you guys memorize, but it is something that you should know. Why is this property written the way it is? Okay, so the first thing I'm going to do is I'm going to write a little let statement. So I'm going to get rid of this log base A of U and log base A of V. So I'm going to let X equal log base A of U, and I'm going to let Y equal the other log base A of V. Okay, now these are both written as logs. I'm going to rewrite this using my exponential. So this will become A to the power of X is equal to the letter U, and then this one would become A to the power of Y is equal to V. Okay, now what are we trying to prove in the product property? We're trying to prove that we're going to multiply U and V together. Okay, so let's multiply them. So if I multiply UV together, that basically means I'm taking my U value, which is a to the power of x, and I'm going to multiply it by my v value, which was a to the power of y. Now, knowing our exponent rules, whenever we multiply numbers with the same base, they both happen to be a base of a, what do we get to do to our exponents? We get to add them. So this now becomes a to the power of x plus y. So notice that, yes, I started off with two individual logs, and then I rewrote them as exponential, and then I'm kind of using the product, so I'm multiplying them together, and we're still back to just a single exponential. So what I'm going to do is I'm going to rewrite this using logs one more time. So log, and then this becomes a base of a of u v, and this becomes x plus y. Now this is starting to look like this guy over here. Now what did we say x was and what did we say y was? Well, now notice log base a of u v is equal to, I'll replace x with log a of u, and I get to replace the y now with log base a of v. So now we know that the right side and the left side of this product property actually is true based on our proof. Okay, the quotient property proof is pretty similar to this. The power is a little bit different. And I may or may not show you that in a different video. Okay, so what can we do with these properties? So there's two things that we can do. We can either expand them or condense our logs. And this is going to help us when we start to solve equations. Okay, so when we expand them, essentially what we're doing is we're creating many logs. Okay, when we condense, we're trying to condense into a single log. Okay, so what we're going to focus on first is expanding. So we're going to do two examples of expanding. And when we expand, we do not want no fractions, no multiplication, no exponents. We want to get rid of all of that. Okay, none to all of that. Once I get rid of all that, I know I'm done expanding. Okay, so if I take a look at my first example, so log base 3 of 6 times x to the power of 4 times y. So I don't see any fractions, so I can kind of skip the first one. So what I'm going to do is I'm going to break up the 6, the x, and the y. So this becomes log base 3 of 6 plus log base 3 of x to the power of 4 plus log base 3 of y. Again, the 6 and the y, these are not exponents. These are the numbers next to the log. So if they had an exponent, it would kind of look like that second log. Okay, we don't need to break up the 6 into 2 times 3, so we don't have to worry about composite numbers. We do have to take away that 4 in the exponent of this x, but we don't have to do anything to the y. So we have one more step, and then we're done. So the 4 comes down, and we get to multiply it, and then nothing happens to the last one, so we're done. So again, we've gotten rid of any multiplication, we've gotten rid of any exponents, and we didn't have any fractions to begin with, so we're done. All right, so let's try the second one. Also notice that we all had log base 3, so notice that all 3 logs had a log base of 3. Okay, so let's try our second one. So I do notice a couple things. I see a fraction, I see some exponents, I see some multiplication. So I'm going to break up my fraction first. So this is going to become log base 5 of 3x squared minus log base 5 of y, and then the square root of z. Okay, so I see the 3 is being multiplied by the x squared. So I'm going to go ahead and break that up using addition. Okay, and I also see that the y and the z are also being multiplied, so I also want to break that up, but I want to make sure that they always stay together. I want the y and the z to always come back, so in order to make sure, I'm going to put these in parentheses, so that way order of operation tells me I'm always going to do my parentheses first. So that's why I'm going to put those together. If I don't, then the z would actually make it to the numerator. Okay, if you want, you can also put the first part in parentheses, but there's no reason to. Okay, log base 5 of 3 has nothing attached to it, so I'm good. This has a 2, so I'm going to bring that apart. And then minus, again, parentheses, log base 5 of y. Now, this is where it becomes tricky. This radical is actually a fraction. This is really z to the power of a half. Okay, why it is z to the power of a half? Just a quick little review. If I took the square root of z and I want to know what does z have to be in order for these two to be equal to each other. So that's the question of the hour. So what I would do, I'm going to rewrite it again over here. And how I undo a square root is I square both sides. So this becomes z is equal to z to the power of 2x. I set my exponents equal to each other. This has an exponent of 1. And then all of a sudden my x is equal to a half. So I now know that these two are equal to each other. So that's how I got the 1/2. It came from your integrated 2 class. So I'm going to go ahead and bring that down. So again, nothing to be done with the first, second, or third log, but my last log, I'm going to bring down the 1/2, log base 5 of z. So this is a perfectly acceptable answer that I'm highlighting, or I should say circling. Whoop. You could also, if you wanted to, you could distribute that negative. So if you wanted to write it like this, log base 5 of 3 plus 2 log base 5 of x minus log base 5 of y minus 1/2 log base 5 of z, you can do that as well. Okay. All right, let's try condensing. So how can I make it become a single log? So let's take a look at 2 more problems. So here's the first one. We see -2 natural log of x plus 5 natural log of y minus 4/3 natural log of z. So what I'm going to do is I'm actually going to bring up the exponent and I'm going to include the negative with it. So I'm going to rewrite the 4/3 as really plus a -4/3. So what this will look like is this will look like the natural log of x to the power of -2 plus the natural log of y to the power of 5, and then plus the natural log of z to the power of -4/3. So the reason I did that is now I've just made everything become an addition sign, which means all of these are being multiplied. So natural log of x -2, y to the power of 5, and z to the power of -4/3. Now, if we recall back in our earlier classes of integrated, we learned that negative exponents, we want to change those to become positive exponents, right? So x to the power of -2 is the same thing as saying 1 over x squared, okay? And so we kind of flip this fraction upside down, okay? So anything that's negative is basically going to go into our denominator. So x to the power of -2, that goes to my denominator, becomes positive. Y to the power of 5, that stays positive, or it is positive, so it stays in the numerator. And then my z can become positive 4/3 in the denominator. So this is a perfectly acceptable answer. Now I always get a few questions. Well, I notice that there's a fractional exponent. Can I leave it like that? Absolutely. If you want to, you can write this as this. Y to the power of 5 in the numerator, x squared, and then this will become the cubed root of z to the power of 4. So if you want to write it as a radical, you can, or you can just leave it as a fractional exponent. All right, let's look at example number 2. So notice that there are, again, 2 subtraction signs. So again, these 2 things should be in the denominator. So we start off by bringing everything up as an exponent. So 1/5, y to the power of 5. This becomes now a plus, log base 2 of z to the power of negative 2, and there is a number in front of it. It just happens to be the number 1. So now it becomes negative 1. They're all addition signs, so let's write this as one single log. And then anything that was negative can now drop to the denominator. So the x stays on top, the y stays on top, but the z and the 5 move on the bottom. And again, I see that fractional exponent, so if we want to, we can write this as the 5th root of x, y to the power of 5. And if we want to write the 5 first, you can do that as well. So we can say 5z squared. Either one, perfectly fine as an acceptable answer. So I'll highlight both of these this time. Okay, last but not least, what I want you to do is I want you to try some of these problems out on your own. You can pause the video and try them out. I starred number 2 on the expanding because this one I didn't show an example of. So that might give you some difficulty. But again, pause the video, try these out, and then when you feel you're ready, unpause the video. I will do the expanding first, 1 and 2, and then I'll do the condensing 1 and 2 in case you want to pause it one more time. Okay, so if you've tried these out, this is what we should get. Okay, so for number 1, I see there's a fraction, so I'm going to break up my fraction using my subtraction sign. I see there is an exponent. Notice it's around both the 3 and the x. So that's going to be very important in just a second. So I need that 2 to be together with the natural log of 3 and the natural log of x. So if you wrote this out, 2 natural log of 3 plus natural log of x minus the natural log of 4, perfect answer. You could have distributed the 2 in something like this. So that way we don't need the parentheses. Now, a few of you might have noticed the 2 could have been with the exponent on that 3. So if you said 3 squared, you could have also, I guess, written it like this, 9, and then plus 2 natural log of x minus the natural log of 4. I imagine most people would have written it these 2 ways, though. All right, so what about number 2? Why did I star it? It looks a little different than everything else. Remember at the beginning of the video, I kept saying the word monomial. Notice this is not a monomial, it's a binomial. So you probably looked at this and was like, all right, well, I know for sure I can do this, can separate the fractions together, okay? And it looks like I should be able to separate the 3 and the x since they're being multiplied, but here's the kicker. There's a minus 5 attached to it. So there's no way I can take away the 3 and the x and separate those without doing something to that 5, okay? So things to remember is you can't simplify a binomial. There is no such thing as the difference property. There's no such thing as the addition property. We only have the product property, which tells us we can add 2 logs together, or the quotient property, which tells us we can subtract these 2 logs together. These aren't 2 logs. This is still a single log, right? So there's not a log just attached to the 5. So this is actually all you can do. Right? So I know it kind of looks challenging, looks hard, but it actually only required 1 step. All right, let's try condensing. So I'm going to bring all of the exponents up. So this becomes log x of 1/3, and then plus log y of negative 2, and then log of z of negative 1. Bring them all together. Okay, and then we have to get rid of our negative exponents. So this will become 1/3, x power 1/3. My y squared moves to the bottom, and same thing for my z. If you ended up writing it using a radical, this would have been the cubed root of x, and then y squared and z on the bottom. So again, either one of these answers is perfectly acceptable. All right, last but not least, condensing. for number 2. All right, so the first thing I'm going to do is inside the parentheses. So that is going to condense to log of x, y. Now, when I do this, I don't necessarily need the parentheses anymore. So I can kind of drop them. So bam, bam. So then I'm going to bring the 1/2 up. Now, this is where parentheses are going to be important. I need to bring that 1/2, and it needs to go to both the x and the y since there are parentheses in the original problem. So this is a perfectly acceptable answer. If I wanted to change it to a square root, I can. So it'd be log square root of x and y. Or if you ended up writing it like this, I could distribute that exponent to both the x and the y. Again, I imagine most people did what it looks like on the first one, or maybe the second one. But again, 3 different ways that I could have written number 2. And that is how you expand or condense some logs using our 3 properties.